So we were just discussing this at during the conference, and most people expected that binary neutron star mergers, it would take 8 to 10 mergers before we found an electromagnetic counterpart. But as you have already heard, right in the first merger which was detected, it was amazingly close. It was just 40 megaparsecs. That's about 130 million light years. Whereas usually you expect farther ones to be just by the volume, you expect to see something that is further away, maybe closer to 70 or 80 megaparsecs. And on the other hand, we also saw really bright electromagnetic counterpart. So here's the map. I think you have seen some of these plots before. In the lower panel here, you see the gravitational wave strain signal. On the y-axis is frequency and x-axis is time. But in the 3 panels above it, you actually see the corresponding count rates measured by various gamma ray detectors. So at the top panel is the low energy part of Fermi, the middle panel is high energy part of Fermi, and the third panel is integral. And you can see that there is a burst that is seen here that comes about 2 seconds after the actual merger. But this is still close enough that we can actually say that these two are related events. And this is what really triggered the entire electromagnetic follow-up, saying that there is not only has LIGO detected a binary neutron star, which we expect will actually be related and will give electromagnetic emission, but beyond that, we have also gone ahead and actually detected this emission. So that's fantastic. And well, Fermi and integral detected it. AstroSat actually is more sensitive than both of these detectors for detecting these kind of bursts. But we did not see anything. And that sounded a bit surprising, but the answer to that is quite obvious. If there's a bright event and you don't see it, it means it is hidden behind a curtain. And in our case, the curtain was actually the entire planet itself. So this is a complicated plot. Let me explain what's going on here. The orange region, orange or brown region marked as GBM here, is the area of the sky where Fermi said the burst must have come from. So Fermi has rather limited direction sensitivity in these energy ranges, especially for such a weak burst. So it marked out an area which was about a few hundred square degrees in the sky and said that the burst must have come from somewhere in this direction. Then the blue band running across the sky here is actually from something called the IPN, the Interplanetary Network. And this essentially was a combination of Fermi and integral using time delay to map it. So this is very similar to what is done by the two LIGO detectors itself. And then you see that the right side of the sky here is shaded gray, and the left side, this white circle here, is the part of the sky which was actually occulted by Earth, which was eclipsed by Earth. And so this is a limit put by AstroSat saying, look, if it was in the right side of the Fermi region, then we would have seen this burst, and the calculated significance is actually very, very high. We would have seen it at about 10 sigma. But since we did not see it, it means that this is where it must have been located. And then you see the dark green close-up at the center. That is where the final LIGO plus Virgo region was. Now, you also see a dashed green set of arcs here. This is one arc in the middle of the map, and there's a fainter arc, part of which is seen at the bottom. This was just the Hanford plus Livingston 2 LIGO localization. But since Virgo did not see anything, that allowed us to eliminate this entire lower arc and also large parts of the upper arc and come down to a much smaller region. We'll ignore the rest of it, but I do want to acknowledge that Arvind, who's an ICER Pune student working at IIT Bombay, did all of this analysis for the AstroSat non-detections and also the upper limits for all other AstroSat observations for gravitational waves. So next in line, the next Indian observatory that we got on sky was actually Hanle. Now, some of you may remember that at IAGRG meeting in Ayuka, I had placed a challenge that it's very, very likely, just from Murphy's law actually, that when the first detection happens, the Eastern Hemisphere might be the first one to see it. And that's simply because most of the large telescopes sit in the Western Hemisphere. And that is indeed what happened. The trigger came at around 7 or 7:30 p.m. Indian time, I was nicely sitting at home thinking that the day is done. And when I read email, it was suddenly time to run around. So we made a bunch of phone calls. And the first thing that we had was, so this again is an all sky map. The pink regions marked at the bottom are the Fermi localization regions. But apart from that, there is a whole lot of gray circles which are marked here. And these are neutrinos which were detected by IceCube, the Antarctica-based neutrino observatory. And these were neutrinos which were coincident or within just a short time span of the gravitational wave trigger. This is all happening before LIGO gave us a refined sky map. So what we did immediately was we followed up several of these locations using the Himalayan Chandra telescope, the 2-meter telescope at Hanle. And we did not find any interesting counterpart or any counterpart at all in any of these fields. Now, by the time we were done with this, LIGO did come up with an improved localization. So here is the green patch again at the center of the image. And it turns out that none of these neutrinos actually came from the LIGO patch. And by the time this was done, the patch had already set from India. So the next place which could have taken data was, which has telescopes, was South Africa, but none of them responded either. And the first telescopes that actually responded were from Chile. In the following days too, we could not get data for two reasons. One is this little smiley sun sitting here. The source was barely 60 degrees from the sun. And it is also very far south, about -30 or -34 south, which meant that it was not accessible from any northern observatories or from most northern observatories. So moving on, here's the first LIGO sky map that we had. This is essentially just the antenna pattern of Hanford. As someone asked in the previous talk, there was a glitch in Livingston, which meant that the automated algorithms had initially just excluded Livingston data from any localization procedures or any detection procedures. And based on this entire sky map, we really had the best bet at this point was to follow up neutrino locations. So to give an example, and then of course, when we got the refined position, it went from that entire all sky probability to this little corner here. So if I were to give an example, it is like putting your best fielder at square leg and the batsman is hitting at cover instead. There's really nothing that we can do about it. But that's exactly why this is a team game, and I'll come to it in a moment. We had a great team of various astronomers spread around the world, and all of us have actually put together quite a good picture of what is going on here. So here's the counterpart discovery itself. It was discovered by a 1-meter telescope located in Las Campanas in Chile. The source was just offset from a galaxy NGC 4993, and it was reported to be pretty bright. 16 detailed photometry later actually decreased the brightness a bit. It was about 17th magnitude. And here are the images. So this is an image which was taken by a small 40-centimeter telescope. So that's the kind of telescope that you could see with amateur astronomers, with good amateur astronomy clubs around the country. And this is an image taken about 10 or 11 hours after the LIGO event itself. And you can see that the source is clearly visible here and not visible in the lower image. Here's a nicer picture. This is taken by our collaborators using the Hubble Space Telescope. So at the center here, you see the galaxy. You can probably, I don't know what the quality of projection there is, but you can probably see a few dust lanes in the galaxy as well. This is an elliptical galaxy. And out here in the upper left, marked with these two lines, is the counterpart which was found by SWOPE. So the first name given to it was SSS17A, which stands for SWOPE Supernova Survey, just named by the Discovery team. And later it was given a generic identifier called AT2017GFO, that is just a sequential character generated which tells you what is the number of the transient in this year, essentially. And here's a story of all the ground-based follow-up. So the first observations, as I said, came from Chile. That's on the left side. This map is showing you day and night, and when each telescope actually took observations. Red circles are observations by optical or infrared telescopes. Green squares are observations by radio telescopes. So you see that GMRT is pretty active. And you can also see that most of the observatories are located in the south. They observe as soon as the sun sets, but they cannot take any data after that. That's because the source sets in less than an hour after the sun. So we'll speed up the movie a little bit more. Follow-up continued for almost 45 days. In fact, there's something interesting in radio that GMRT is still following this source up because the radio is still expected to get brighter over time. So this again was put together by our team. The animation was made by my student Pawan Hebbar, but we have this growth collaboration, which is 7 countries, 15 institutes working together on exciting transients like this one. So here's the next detection. Swift followed this up. Again, unfortunately, this was too close to the sun. We could not point astrosat to this, but the image on the left is taken just a day or so after the explosion. The image on the right is taken 6 days later. Image in the middle, and the one on the right shows a close-up, and here's the source. So it was bright in UV. This was quite unexpected from various kilonova models, actually. There were some models, of course, that predicted this would happen, but most models seem to suggest that it would not be bright in UV. It would be a pretty red transient. And another surprising thing was that if you have an explosion, you expect that it will be bright, and whatever light it is going to emit is going to be bright initially, and it is going to keep fading off with time. But when people tried to observe this with Chandra, Swift and astrosat didn't see anything. In fact, Chandra also did not see anything about 2 days after the explosion, but they went back a week later, so total 9 days after the explosion, and they found the source, and it was still present 15 days later. After that, it went too close to the sun even for Chandra, so we'll have to wait for another month or so for more follow-up. But these are quite some puzzles about what exactly is going on in the source, and probably you'll hear a bit more about this in the next talk. Here's the radio detection seen with VLA, the very large array. This is seen at, I believe this is a plot at 6 gigahertz, but it was also seen at 3 gigahertz. The big blob at the center is the galaxy, and this faint source just to its upper left is a new source not seen before, and it is exactly at the coordinates of the kilonova. With GMRT, I said there's an interesting story, and that is when you go to longer and longer wavelengths, the emission actually becomes brighter later and later. So this is true even in optical. It was seen to be blue short wavelength emission first, and then it became redder. But similarly, in radio, it was first detected at 6 gigahertz and then at 3 gigahertz, and there is still no detection at 1.4 or at 600 megahertz, which is where we are observing GMRT. But this lack of early time emission actually has been capitalized upon by 2 groups. One is our group, and another group had Reshmi, Kuntal, and others. So both of these collaborations actually have used GMRT upper limits at low frequencies to rule out certain classes of jet models for the ejecta from the kilonova. Remember that GMRT even now is the most sensitive radio telescope at low frequencies in the entire world. So what exactly is this object? And, looking at the picture right now, it seems quite, we take it for granted that, astronomers saw kilonova, they saw a gamma ray burst, they saw a GW event, but these are really 3 distinct events. We saw something in gravitational waves. Within 2 seconds of that, we saw a high energy trigger that was detected by gamma ray burst detectors. And we saw an afterglow, something which happened to be in that direction of the sky and kind of looks like an afterglow of the GRB. But how can we be sure that these 3 really are the same thing? And that is essentially what took a lot of effort. And that is why there were about 70 different observatories that were involved in this follow-up to prove that these really are one and the same thing. So let's look at a comparison between the gravitational wave event and the high energy trigger. So we saw something in gamma rays and in gravitational waves, but what are the odds that these could just be 2 unrelated events which happen to be close in time? And there you have to define your time requirement at first. how close do they have to be to each other or in time so that you could actually call them the same event? And usually the interval that has been used by various observatories is about 100 seconds. So we detect roughly one gamma ray burst per day, all observatories put together. And 100 seconds is about 1,000th of a day. So if I give you a random 100-second window in the day, then you have only 1 in 1,000 chance of finding a GRB in that. On top of that, then Fermi plus AstroSat plus integral together narrowed down the part of the sky where this source is located, and it matched the gravitational wave localization as well. So what are the odds of this happening? Well, the sky is about 41,000 square degrees, and all of us together brought it down to under 100 square degrees. So that's again a factor of 500 to 1,000 that you get there. So all in all, the chance coincidence probability of this is roughly 1 in a million. So you can be very, very sure at 99.9999% that these two events are actually the same event. And then comes the afterglow that was seen in optical, X-ray, radio. What else could it be? We know that there are a lot of transients in the sky. We know there are supernovae, there are novae, there are flare stars. Gamma ray bursts have their own afterglows. So answering this question and proving that this was really not like any other afterglow took a lot of effort. We had to monitor this for a long time. We saw that the spectra don't look like novae or supernovae. The light curve, the way it changes in brightness and in temperature in different parts of the electromagnetic spectrum it matches pretty well with kilonova models, but it does not look like any other known transient. So here's an example where what is plotted is along the x-axis is wavelength. So blue light is and UV are at the left, and at the right side we have infrared. And as a function of time, you can see that the source, so I'll play this movie again, and you can see that in the beginning, the source was actually bright, uniformly bright from blue to infrared wavelengths, and it was a bit fainter in UV. And as time evolves, you'll see newer observations popping up on this. The source faded away very quickly in UV, and then it started fading in the blue wavelength. So somewhere here is red light, around 7,500 angstroms is far or very near infrared or far red. And you can see that the source was actually going from blue hot to red hot. So that already tells you that this is something which is cooling. And it is better seen in spectra obtained from various telescopes. So here are spectra. The first one is taken by SALT just 1.2 days after the explosion. And it kind of looks like a hot black body. The black body fits are much better to just the photometric data, which I showed on the previous plot. And on the first day, it looked like a black body at about 8,000 Kelvin. And then over a few days, just a period of 2 to 3 days, it faded down to a black body. If you can't read this clearly, it says 4,000 Kelvin. And eventually, people followed it in a black body-like shape until it came down to about 3,000. But what is also interesting is you see these wiggles in the red spectrum. And these wiggles are actually what were theoretically predicted as signatures of R-process nucleosynthesis elements. So half the elements beyond iron are all formed in such events. So gold and platinum, for example, practically all the gold and platinum in the universe are postulated to be found by colliding neutron stars. And this is the first time ever that we are seeing any observational signature that merging neutron stars actually produce such elements. So what is the meaning of it all? Well, I'm not going to go a lot into the interpretation. You'll hear it more about this in the next talk. But let me try to address one little thing. Why did the gamma rays come 2 seconds after the merger? So here's the model that our growth collaboration actually thinks answers this question the best. Sorry, you're not going to hear Brian Metzger's talk. I copied this slide from another talk I gave here a day ago. So what is shown here, currently seen in the reddish and bluish colors, are material from the neutron star that was tidally stripped before the two neutron stars collided. So it forms a kind of envelope around the two neutron stars which are going to collide at the center. And when I play this movie, you'll see a jet being launched from the merging neutron stars. And this jet now actually propagates through this envelope. And it's only when this jet actually breaks out of the envelope that you start seeing the flashes in multiple wavelengths. So this is why you see the gamma ray burst itself slightly later. And this model also predicted that X-rays would become visible about 5 to 8 days after the collision itself. So there are several Indian co-authors on this paper. We have published this in Science, and it's available online. Currently, Science has made these papers free. So in the last few minutes, I'll come to the future outlook. What can we expect going forward in the field of electromagnetic follow-up to these sources? We have been talking about this for many years in India now and around the world, and we finally have first flight. And it is important to realize that there was huge importance of collaboration here. So our own collaboration, as I said, had 15 institutes, but everything put together, the LIGO plus Astronomers Multimessenger Astronomy paper has 3,500 authors from about 950 institutes around the world. They have identified themselves roughly as 48 groups. Now, these groups often have subgroups, so it can keep going. You can keep going down the rabbit hole here. There were about 70 observatories, radio, infrared, optical, UV, ground-based, space-based, everything, that used more than 100 different instruments in order to follow this up. And it's only because of all of these efforts being put together that we could actually conclude that the three signatures that we saw, the gravitational wave event, the gamma ray burst, and the afterglow, are actually one and the same thing. Now, from the Indian perspective, in the future, well, AstroSat CZTI has actually been giving us some of the best upper limits in the world on various binary black hole candidates that we had been detecting so far. In this particular case, the source was behind Earth, but even that allowed us to localize the source better than what just Fermi had done. Also, you see a picture of an optical telescope here. This is the telescope which we are setting up in Ladakh as a part of the Growth India project. And this telescope itself is actually already on the mountain. We hope to commission it later in this year. So it should become fully operational by the end of 2017. And this is a 70 centimeter telescope. I'll remind you that some of the detections were done by much smaller telescopes. So if you put in the numbers, it turns out that this is great news for us. We are sensitive to about 21 or 21.5 magnitudes. And even if you take this kilonova and move it all the way to the horizon, to the sensitivity distance of advanced LIGO, so you put it at around 200 megaparsecs, the source will still be visible to our telescope. And this is going to be fully automatic. As soon as LIGO sends out a trigger, it won't wait for us even to click on go. It will just start off by itself and start observing that region in the sky. Here's the team. A lot of work is being done by the students. Apart from myself and Anupama, who I believe might be in the audience just now, we have students from IIA and from IIT Bombay who are working on the commissioning and automation. They've been working really hard in getting this done. So I'll end with that simply by saying that this is great news for us and the future is really bright for EM follow-up. Thank you.
Thanks, Varun. Any questions for Varun?
Hi, Varun. This is Sukant. Thank you for a nice talk at midnight. A couple of questions. The first one, regarding the last thing you said about limiting magnitudes. We worked on this together, right, on limiting magnitudes predicted for kilonovae, and we found it to be very difficult for objects at 200 megaparsec. Not impossible. I mean, there are claimed kilonovae detections even beyond 200 megaparsec. But is this particular kilonova something different or atypical? That's my first question.
So far, we have not seen any indications that this could be a weird or peculiar event. Of course, we are talking with very small number statistics, exactly one detection to date. This kilonova does sit very close to the bright end of all kilonova models that were out there. So people had predicted that for a kilonova at around 200 megaparsecs, the peak magnitude could be anywhere between, say, 20 to 24. And for this one, it would be about 20.5. So if kilonovae do turn out to be like this, then that's great news. I've been hearing more talks about this at this conference I'm attending right now. And it seems that the consensus will probably emerge that there is something called a red component of the kilonova and a blue component, which are visible from different viewing angles. So there will be debates about some kilonovae might fade out faster than this one, but very likely we will see this kind of brightness for most kilonovae.
Thanks. Can I ask another quick question? This second one is on Metzger's slide. So I'm going to put you on the spot there. You mentioned 14 point some seconds for the breakout, right? And you perhaps gave the impression that this is related to what, X-ray emission? I mean, gamma rays obviously came out within a couple of seconds. So are you sure this jet is really the gamma ray jet, or is it more likely the tidal disruption that can generate, our process nucleosynthesis and kilonova emission?
Well, there are a lot of different models that attempt to explain all of this, but what we believe right now explains all of this pretty well is that the jet which is launched by a conventional GRB kind of gets choked by all the material that is sitting around it. Now, if you happen to be on axis, you would still see it as a conventional GRB. So there are probably places in the universe where you could have gone and seen this as a normal GRB. But for off-axis observers, one possibility is that you are just sitting outside the jet and you have, that's why you see the emission later, something like a jet breakout, but that requires a lot of fine tuning to get it work as a regular off-axis GRB jet. So what then you have to do is you have to have some mechanism of choking the jet for a little bit, and then that slows down the jet drastically. So this has a gamma of about 1 or 2 rather than of 100. And then when this breaks out, it forms this cocoon. And when the cocoon breaks out of the tidally disrupted material surrounding the merger, that is when you start seeing all these emissions. And the part of the cocoon that was in the direction of the jet gives you this blue kilonova, which is coming, which is primarily powered by free neutron decay and then followed by beta decay. Whereas material which is in the equatorial plane is giving you the red kilonova that is dominated by our process nucleosynthesis. So there is high opacity from all the lanthanides that were generated, which send all the which take all the blue photons and reprocess them out into the infrared.
Thanks.
Hi, you mentioned that there were 6 neutrino emissions which were proximal in time but not really in space. What does it really tell about the source of this event? Were they expected to be seen, or?
Well, we don't know if we will get neutrinos from binary neutron star mergers. This one at 40 megaparsecs, I would have been very, very surprised if we saw neutrinos from this. For comparison, we don't expect to see neutrinos from any supernova that is not within our galaxy or within our satellite galaxies. So, all it tells us at this point is that the neutrinos were not related to this. They may have been astrophysical in origin, but they were clearly not related to this one. Also, IceCube uses a larger window. I said that most gamma ray telescopes use a 100-second window to define it as coincidence with binary neutron star merger. But in our case, in case of IceCube, they use a 1,000-second window. So you are 10 times more likely to find something by random chance.
Hello, Varun. Great talk. Thanks. This is Rajesh Gopakumar here. I just had a question. Would all these electromagnetic counterparts, would they be able to shed some light, so to say, on the remnant? You didn't mention very much about what the final object would be, and I've read things about it could have been a black hole because it's more than 2.5 solar masses and so on. Would one learn something about this at some point or not?
I think we will, and I think actually we will learn something about it from EM follow-up before we do from LIGO. And the way we will learn something about it is that so there are 2 things that can happen. Well, first thing is that from a GW perspective itself, right now, just the LIGO data would not have been able to rule this out as a merger of 2 1.5 solar mass black holes, for instance. So the fact that we see all of this electromagnetic emission tells us that there is at least one neutron star involved. And the fact that it matches kilonova models reasonably well tells us that very likely we are seeing 2 neutron stars that collided, not just one. Now, the question is what happens to the merger remnant? Well, there are some models in which you form a proto-stable neutron star, which can last for a few hundreds of milliseconds in the most extreme cases before it collapses into a black hole. And that changes the nature of the prompt emission that you expect. It also changes a few details about the kilonova that you can see. But the modeling so far had been done in just as blank modeling. We had no observational data to fine-tune the models. So as we see a few more of these events and a few more kilonovae, we actually expect that the models will get more refined and we will be able to predict and see differences between whether a proto black hole was formed, whether a quasi-stable neutron star existed for a little bit before collapsing into a black hole.
One question. What are the length scales at which the jet breakout happens with respect to the radius of the star?
With respect to the radius of the neutron star, if you are looking at the cocoon model, it is actually much farther out. So let me bring up that slide again. Let's see. You can see the length scale that is marked here is actually about 10⁻11 centimeters.
Okay.
Whereas the neutron star diameter itself is going to be about 25 kilometers. So this is much farther out as compared to the neutron star sizes themselves.
Thank you.
Okay, I think let's wind up this session. So thank you, Varun, once again, and good night.